Let's take a look at some of the basics of a 4 to 20 milliamp current loop system. The pros. The 4 to 20 milliamp current loop is a dominant standard in many industries. It is the simplest option to connect and configure. It uses less wiring and connections than other signals. Greatly reduces initial setup costs. Better for traveling long distances, as current does not degrade over long connections like voltage. It is less sensitive to background and electrical noise. Since 4 milliamps is equal to 0% output, it is incredibly simple to detect faults in the system. Some of the cons. Current loops can only transmit one particular process signal. Multiple loops must be created in situations where there are numerous process variables that require transmission. Running so much wire could lead to problems with ground loops if independent loops are not properly isolated. These isolation requirements become more complicated as the number of loops increases. 4 milliamps represents 0% input level, allowing underscale fault detection. 20 milliamps represents 100% input level, allowing overscale and fault detection. In our 5-volt system, we use a 230 ohm resistor. In a 3.3 volt system, we normally use 150 ohms. We do that for the reason we want to be able to measure above and below the 4 to 20 milliamp range for fault detection. Here we have the most common 4 to 20 milliamps wiring schemes. We have the 4-wire and the 2-wire system. The 2-wire, we have the power supply powering the loop through the transmitter back to the PLC. We also have the 4-wire system where we're feeding power into the transmitter, and via the transmitter it's powering the loop, our 4 to 20 milliamp loop, to the PLC. A 3-wire, which is not that common, where we run a wire from ground, from the power supply to the transmitter. In a sense, we're powering the loop and applying some voltage to the transmitter in the case of a 3-wire. Sensor that we're going to be dealing with today, 4 to 20 milliamp output for water, gas, oil, 0 to 1.6 megapascals. Processor, we're going to be running Nano. We're going to be running one of the newer Nanos, 33 IoT, and this is kind of a description on how it fans out against the standard Nano. You have more memory, more processing power. You have a 12-bit ADC. You have Wi-Fi capability, and you also have a DAC on the 33 IoT. And we're going to be measuring current directly with a Adafruit INA260 current sensor. It includes a precision shunt resistor, can measure 36 volts at 15 amps continuous current, either on the high or low side. It includes an internal 16-bit ADC, measuring voltage across a 2 milliohm 0.1% shunt resistor. The module also offers programmable conversion times and averaging modes. To achieve the highest accuracy, use a combination of the longest allowable conversion time and the highest number of averages based on the timing requirements of the system. And we'll look at that tuning also when we get into the code. And this is a breakdown of our system. The wiring, our sensor, the Arduino Nano 33 IoT, our INA current sensor, our monitor, monochrome monitor pinout, and another diagram of the circuit we'll be going over, the LM317 constant current source. We're set up now to get our baseline readings from our 4 to 20 milliamp loop circuit here we have set up. We have 24 volts feeding into the board, into the sensor, through the sensor, out through the sensor, through our 250 ohm resistor, through a diode, back to ground. So we're going to pressurize it now. We're looking like we're sitting at 1 volt divided by the 250.7 should equal approximately 4 milliamps. So we're going to take that reading and we're going to apply pressure from our nitrogen bottle. And we're going to take it up to 240, and then we're going to move down from 240 to 210, 180, 150, 120, 90, 60, 30, and back to 0. So we're going to open up the bottle here, our nitrogen bottle. Our valve here is closed, and let's feed it some pressure. Take it up to 240. Almost there. And we'll overshoot. We'll bleed off a little to get it back to pressure. Close off our bottle now, and we'll bleed off a little to get it back to 240 exactly, or as close as we can get it. 240. And we're going to record that. 210, and we're going to say 4.5. Yeah, bleed off to 180. Yeah, about 180. We're going to call that 3.98. Bleed off to 30. 30. 1.48. 10 psi. 1.25. And we'll calculate those out to pressure by using our 250 ohm resistor, 250.7, and we'll plot those numbers out. We have our data entered now onto the graphics calculator, so let's take a look at it. These are the data points that we entered versus the perfect linearity. If it was perfect 4 to 20, that would be our red line, and this will be our blue line. So let's take a look, see how it graphed it out. Okay, perfect line, the red line. The blue line is the line of best fit, and most of all our data points fit on the red line. So the linearity is good, and we should get good data out of our sensor. We now have our 4 to 20 milliamp circuit set up. We have our 24 volt power supply powering the system. So let's apply some pressure, and we'll check it out and see how it works. Close the valve here. We're going to be using a nitrogen bottle for the pressure. Bring it up to pressure. We'll start out looking at it right now. 0 pressure. The valve is, make sure it's open. No pressures on the system now. 3.9, 0 psi. Essentially 4 millivolts or milliamps flowing through the circuit right now. We'll close the valve, give it some pressure, and we'll slowly take it up to 240. Reposition this hose line here. Okay, bringing the pressure up. Get it as close to 240 as we can. See what the thing reads. A little tad more. There's 240. Close the valve here, back it off. Okay. See how that looks like we're a little tad above 240, but let's see what it reads once it settles in. Here's our 20 milliamps. 39, 240. 240 on the gauge. This may be a little tad more. We're reading 241 on the gauge. Yeah, 240, maybe a hair above. So that's pretty close. Let's back it down. We're going to go all the way down to 0. Take it down to 210. Carefully let some of the pressure out. 210. Let the Arduino settle in. And 210 on the gauge. 212. 214. 213. Okay. That's close. It's not perfectly linear, but it is amazingly close. Let's take it down to 180. I remember the 180 mark was a little bit off the line of best fit, so it may be a little bit more off. Not quite as linear, but let's see. 180. 180 on the gauge. Let the Arduino settle in. Okay, yeah, we're right on 180. 185. 184. Okay, close. Let's take it to 150. And like I said, that 180 point was a little bit off the line of best fit when we did the equation. So 150. Let the Arduino settle in. 150 still on the gauge. 152. 151. 150. 149. 149. Okay. 150. Okay, that's close. Let's take it down to 120. Easily let some of the pressure out here. Okay, 120. 120 on the gauge. It's still coming down. See where it's going to settle out at. 120. 126. Oh, looks like it's going to settle out at 124, 125. Let's take it to 90. Okay, 90 psi. 94. We're still showing 90 on the gauge here. Oh, 93. 92. 92. 93. Okay. Let's go for 60. There's 60. That's settling in here. 59.60. 59.60. Okay. 61. Okay. Let's hit 30. That's 30. 35. Let's see, it's still on its way down there. It's going to settle in. See where it settles in at. 131, 132, 133, or 33 rather, not 133. 30, 32, 30, 32, okay. Well, let's take it all out, take the pressure out, rest it back at 0. Should give us a 0 at about 4 milliamps. Okay, it's still working its way down. 4 milliamps. We'll probably bounce around like we started out between 4 and 3.9. Okay, did pretty good. It's not 100% linear, as we saw when we did the equation, but the data points are best line of fit, so it's pretty close. And here we're going to take a look at some live data coming in from the sensor, looking over at the data over the last hour. And we could pick any point on the line and see what that point was with the date and time, pressure, date and time over the last hour. Real time and historical data. Day out. Back to 1 hour, past hour. Back to the live data as we move up from 130. Or actually that'll be the moving down to 130. This is our most current point. date and time at any point we want. Check our pressure levels. All part of the IoT capability of the Nano 33 IoT. Real-time live data and historical data. Out to 15 days. The timeline below at the bottom is local time, the time and date above in the box, 129 psi on May 13th. That would be Zulu time. Now we're back in the last hour data. So that's all available to you from the Arduino. Let's take a look at the code. We're going to start off with bringing in some of our prime IoT cloud settings for the Arduino IoT Cloud. Our include statement first, starting off with the Arduino secrets, which is our most of our internet connection parameters. We're going to define the PSI val as a float. We're going to include the things properties, which is part of the IoT Cloud. We're going to include the SPI library, the wire library, the Adafruit INA260 library, our Adafruit graphics library, and our Adafruit OLED library. We're going to set some or OLED screen parameters here in these 4 lines. We're going to set up our low-pass filter at 0.97 to start out with. We're going to set our cow correction to 0.1, and we're going to set a starting point for the current val as 0 to start out with. We're going to set our objects for our INA260 and our OLED display. We're going to name the Adafruit INA260 object as INA260. We're going to go into the setup. We're going to initialize the serial monitor. Then we're going to wait to make sure the native USB port is open. We're going to check and see if we have INA260 installed. If we do have it, we'll print out found INA260. We're going to set the number of samples that we're going to take in our averaging at 16. We're going to set the measurement time to 1.1 millisecond for both the current and the voltage conversion, although we're only going to be looking at the current conversion. We're going to set up our OLED display. We're going to look and see if it's there. We're going to clear the display, get it ready to go. We're going to set some additional things property for our IoT cloud. And these 2 statements. We're going to set our debugging value at 2. Then we're going to go into the loop. We're going to update the Arduino cloud, IoT cloud. Then we're going to read the current into the ADC val. We're going to take that ADC val, put it into a low-pass filter, and it's going to smooth it out. We're going to come out with a current val. We're going to put that current val into our equation, and that's going to give us the correct PSI val. We're going to send that to the serial monitor, and we're going to call the function update OLED, which is going to update our OLED display. And we're going to delay for 200 milliseconds and start over again in the loop. This defines our OLED function, update OLED, in this function. Here at the bottom, I've also included some comments that are essentially a little cheat sheet on the values that you can set as your current measurement times and your sample rate. I'll touch a little bit on the formulas, the equations that we used on line 90, around about line 90 to 93. We have three equations there. The first is an ideal linearity equation, just assuming that the sensors were linear from 4 milliamps up to 20 milliamps. The last two were done with a linear regression calculation, where we took 10 to 12 samples at different readings to determine best line of fit. So those are specific to those two sensors, which came out very close to a perfect linear line. You have an R2 value there, which they call the coefficient of determination. The closest that is to 1, or the closer that is to 1, the more perfect the fit is to a standard ideal linear equation. So you can see there that the last two sensors we did after we took the readings, they were fairly close to 1, 0.9987, the other 0.9988. So in theory, you could just use the standard linearity equation and that would work. But first, let's kind of get a look at that, and we'll go through how that's calculated. The linear regression, you could do that by hand, but that's a little bit involved if you're talking about 10 or 12 individual points that you try to fit onto the line. A single one, we're going to take 2 points, which is the equation for a straight line. We're going to implement that. So we'll kind of draw it out so we kind of get a look at what that actually is. We're going to have our graph here. Going to have a y, an x. We're going to have our points. This is the origin, 0, 0. And on the x, which is our input, normally they consider the y the output, or the domain, or the range, as they're called in mathematics. But our x value is going to be in milliamps. And in this case, our y value, or the range, is going to be in PSI, pounds per square inch, and that's going to go from 0 to 240 on this particular sensor, and 0 to 20 milliamps. So at our 4 milliamp point, PSI is 0, so 4 milliamps is going to represent 0 PSI, or 0, the 0 value of our process variable, which this is called, they call it process variable. So this point here, we're going to label as X4, 4 milliamps, 0Y. So we're going to label that point X1, Y1 for that order pair. And on the high end, we're going to have 20 milliamps up at, close as we can get it, up here to 240. And that'll be 20x, 20 milliamps, 240. That's going to be our X2, Y2 ordered pair. And if we draw a line, we'll see it goes so we have a positive slope. And when we're doing linear lines, equation for a line is defined by the slope, which we call it the slope M equals y2 minus y1 over x2 x1. So what is our y2? Our y2 is 240. Minus y1. y1 is 0. our x2 is 20 minus the x1, which is 4. So we have 240 divided by minus 0, or 240. 20 minus 4, 16. So we do the division, 240 by 60, 16, gives us a slope of 15. So our slope equals 15. Now we have two formulas that we normally use once we find the slope. We have what most people are used to seeing as y equals mx plus b, where b is where the line intersects the y-axis when the x is 0. Well, it would intersect the y-axis somewhere down here in the negative y range. I don't know what that is. We can't really see it, so it's not plain. So this is called the y-intercept form of the line. So I can't determine what that is. So we have another, what we call is a point slope formula form of a line, which is y2 equals the slope onto x2 x1 plus y1. So at this point we can enter, this is our point slope formula for a line, form of the line. And this is an Arduino, this is the map function. That's what you're doing when you're entering, when your input, those first two numbers are your x-axis, and the last two is where you're going to map to, which is the y range. So we're going to plug in the values. So they call it the point slope. All we need is a slope and a point. So we have the slope, so we can replace that m with y2 equals 15 for the slope onto x2. x2 is part of the ordered pair with the y2 that we're going to find. Minus, now we're going to, for x1 and y1, we're going to select a point. It could be either point will work in the equation. If you use this point, a little more math. This one's the least amount of math, so we're going to use this one. We're going to use 4 is the x1 plus y1 is 0. So it makes it a lot easier. We could have used this point, the answer would come out the same. So we can rewrite this as y2 equals 15 onto x2. Since we got rid of the y's, we don't need the designation. All this y to x2 is just so we can designate, we don't mix up the ordered pair. This y goes with this x, this y goes with this x. So now we can just call this y, and this is x. Now we multiply through, minus 60. And that drops out because that's 0, so we have our answer. Y equals 15x minus 60, and that's where we have that equation. If you go look at it, that's where we got that from.